Good day, this is Jim Pytel from Columbia Gorge Community College, Renewable Energy Technology Program. This is EET 122, Digital 2. Today we are going to end our discussion of counters with a grab bag lecture discussing counter applications, troubleshooting, ANSI IEEE dependency notation, and a super brief discussion of the system application activity. Number one, the first application, as illustrated in your book, is a digital clock, which is an excellent example of using frequency division, modulus, and a cascaded arrangement, as well as decoding a truncated sequence, in this case 12, and preloading a 1 on a recycle. So key to the frequency division application is the fact that you're supplying a clock with a 60 hertz waveform, and we're lucky enough to live in a country whose domestic power supply operates on 60 hertz. This particular arrangement wouldn't work in the EU, which is a 50 hertz AC system. Feel free at this point to pause the lecture and wrap yourself in an American flag and sing a patriotic song of your choice. So ultimately, what's coming out here is from this wave shaping circuit is a 60 hertz pulsed waveform. We've gone to sinusoidal to a pulse 60 hertz, both 60 hertz. So now we're going into our frequency division portion of it, and what we've got here is a modulus 60 counter. So it's basically a 60th of a 60, or 1 hertz is coming out here. Basically, you're stepping down to 1 hertz, 1 cycle per second. You're simply feeding that 1 hertz signal into a cascaded modulus 60 counter, the seconds. So 6 times 10 modulus 60, which in turn is cascaded with another modulus 60 counter, the minutes. Because when a clock reaches the state of 5-9 seconds, you want, let's say it was a 0 at 0 minutes there. What happens there, you want to go ahead and the next clock pulse comes along, you want to recycle this guy and increment this one, hence the cascade there. So anytime it reaches 59, it recycles the seconds, increments the minutes. By the way, you're using 7447s, BCD to 7-segment decoders to display each one of these guys here. You get the picture. Each one of those digits. Okay, which finally brings us to the hours display, because we want our hours to increment at, let's say, right here. We want our hours, let's say we're at, let's say 1 o'clock and 59 minutes and 59 seconds. Okay, so next clock cycle comes along. We want this guy to recycle, increment the minutes, but that brings it to its maximum state, 0, 0. We want to, it's cascade, so we're going to increment this guy right there. Okay? So, given the fact that you've got this 1 digit here, the ones digit for a clock, this is the tens digit, you know, you're going to have it go from 0 to 12 for a clock. So what we want to do is make basically a modulus 12 counter. So we can make a cascaded arrangement here of a modulus 10 counter, this guy for our ones digit, and a flip-flop, which if you think about it is a modulus 2 device, and in a cascaded arrangement 2 times 10 is 20, thereby allowing us to count from 0 to 19 if we wanted to, but we don't. We just want to count to 12. So basically what we're going to do is we're going to try to recognize the presence of a 12 using some partial encoding, i.e. when the ones digit is 0, 1, 0, which is a 2, and when the tens digit is 0, 0, 1, but in the case since we're using a 1 flip-flop, we just want to recognize that when that's a 1, because we're using 1 flip-flop. And now what you do is when you recognize that state of 12, all you're going to do an inversion and send that to the active low load. By the way, I'm referencing that picture there, so make use of the picture in your book here. And send the active low load with a 1 dangling off the preset inputs, the data inputs there, off of this guy. So basically, when you get to 12, .59, next clock pulse comes along. You want this one to recycle to 0, which is in turn going to increment the minutes. But that recycles, which in turn increments 12. The next state, it's already recognized the fact that at 12, it's recognizing the presence of the 12, so there's already something hanging off that load. Basically, it's giving an active low load. And what's dangling off the D inputs? 1. It just loads that 1. Pretty cool, huh? Ta-da! You've got yourself a digital clock. So, given all what we've just got right here, you should be able to figure out how to make it a 24-hour clock. And while you spend the next 20 minutes thinking about that, we'll continue on with this lecture. So, second application that I mentioned is a simple counter. Up until this point, we've been running counters on regular clock signals, and every clock pulse it increments. My question to you is, how different would a counter react if the clock was replaced and simply hooked up with a means of detection, let's say a photo transistor, that generated a pulse via a one-shot every time it was triggered? The answer is no difference at all. A positive edge triggered counter would still increment on a positive edge transition. It doesn't matter if it's a regular signal or not. I'm going to refer you to our earlier example of the pill counting device in maybe chapter 1 or something. Every pill produces a pulse, and the counter increments on every pulse. Doesn't matter if a pill is coming out 1, 2, 3, 4, 5, and then there's a super long pause, 6. The counter increments every positive edge of that pulse. And the third application, I'm going to refer you to basically the sharing the same lines multiplexer and demultiplexer lecture from a while ago. In that lecture, I spent a lot of time yapping about the multiplexer and the demultiplexer, but I only briefly mentioned the third device in the arrangement. If you remember correctly, was the counter, which was dangling off the data select lines. Basically, its job was to generate the data select positions from 000, in this case it's a 3-bit, 000 to 111, then recycle back to 000. Okay? So on to dependency notation, ANSI IEEE. So thus far we've been making use of mostly of the distinctive shape symbols, but you should also be aware that there's an ANSI, American National Standards Institute, and IEEE, International Electrical something, IEEE, exists. Basically, it's a standard means by which symbols are drawn. Ultimately, the big picture is there's three different things that you should be aware of when you're using dependency notations and the ANSI IEEE. Blocks. Basically, there's a control block. So the control block has common inputs. And those are normally like clocks, enables, loads, clears, modes, like ups and down modes, things like that, things that affect everybody. The next one is the individual elements. In this particular case, the example in the book is a 74163. It's a counter, 4-bit synchronous counter with, as you'll see, a synchronous clear. These are individual elements. They're basically the inputs and outputs. In the case of this counter, it's the data inputs, D, and the storage outputs, Q. If it was a NAND, you'd get your inputs for the NANDs and outputs for the NANDs. So the qualifying symbol, that's the third thing here, is we've talked about our control elements, or excuse me, our control block, our individual elements, and finally the symbol. Basically, all you're doing is, remember our earlier discussion, distinctive shape symbol of an AND is that. You're just replacing it with a block, in this case, with an AND. An OR is replaced with something that's greater than or equal to 1. Oh, by the way, in this active low or inversion, an ANSI IEEE standard is denoted by a triangle rather than a bubble. So inversion is denoted as that little wedgy looking triangle. That replaces the bubble. Okay. In this particular case, we've got our control block is its particular qualifying symbol for a counter is up here. Counter, in this case, div 16. A little description of what it is. That's all it is. It's replacing these distinctive shape symbols with these guys. Okay, so final thing about ANSI IEEE standard notations is these letters here, C, M, and G. And we'll talk about each one of them in turn. C, M, G. So C. C is control dependency. This is an input or the input that is controlling the chip. Most often it's the clock. The digit, let's say this is our control input here in our particular case for the 74163 in your book. It's got C5. So the digit after the C is what inputs it controls. And like I said earlier about synchronous clear versus asynchronous clear, so let's have an active low clear up here. And I've got that little triangle signal, and that's our clear. It has a 5 in front of it, 5C. So basically what that's saying is it's dependent on the clock. Now, does that make it a synchronous or asynchronous clear? And the answer is synchronous, which is different from the JK flip-flops, which you discussed, which are asynchronous clears. Okay? So control dependency, C, control dependency. That input or output or whatever it is controlled by the thing that has the C in front of it. Okay? M, this stands for mode dependency. And this is only for chips with customizable outputs, like in this case, the 74163, where there's a load mode and just a natural count up mode. Let's just stick with the same example here. We got our load, active low load, which says it's M1, mode 1. And notice, even though there's not another pin there, there's only one pin for load, what that's saying is, make some space here, M2. So when it's in low, when there's a low here, it's in mode 1. When there's a high here, that's in mode 2. Okay? So something else like a 74190, that's our up-down counter, that also has a mode 1, mode 2. Oh, by the way, when there's our control here, C5, 2, that means it's operating in mode 2 when that's a 1. And it increments it to plus. Finally, the third one, which we just discussed, was mode. Third one, G, stands for AND dependency. I know AND doesn't start with a G, but it's CMG. AND dependency means anything with a digit following the G must be ANDed with that input for it to produce an output. Most often, these are enables. I know this sounds a little confusing because we haven't been using ANSI and IEEE. We've just been used to distinctive shape symbols. You're lucky enough to be in a time when most data sheets have both. They have the distinct shape symbols, the ANSI IEEE dependency notation, and they're also nice enough to actually have an English description of it. Short paragraph describing, most data sheets by the way, a short paragraph describing what a chip does in plain old English. So even if you don't know this guy and you don't know this guy, they're nice enough to describe what a chip does. And I'll actually go ahead and put like a PDF for, I don't know, some chip on there. So you can go ahead and take a look at it. Which brings us to the topic of troubleshooting. So quite literally, there's a bazillion ways to get it wrong. And there's oftentimes only a couple ways or one way to get it right. So just the things I want to bring to your attention for troubleshooting, counters in particular. Why won't it count up? Why is it stuck at one number? Why is it not going to the number that I want to? Why, if I've got a truncated sequence, why is it counting to full modulus? So the answer to a lot of these things, two words: opens, shorts. So if we remember right, TTL logic, anytime it's open, it's assuming it's a high. Okay, so for example here we've got a cascaded counter where this one's terminal count is this guy's, oops, excuse me. Yeah, this is our enable right here for this guy. Well, let's say that's a modulus 10. That's also a modulus 10. So basically, this one is a cascade. This guy right here is that's the MSB. It's a cascaded relationship. Only time it's enabled is when this guy says, go ahead and count now. But check this out. What would happen if that was an open? Well, it's, according to our notation right here, it's assuming that's a +5 right there. It's an open. Therefore, this guy, the MSB, is counting the exact same time as the LSB. So it's constantly enabled. Okay, so that's our opens there. Our shorts. Let's say, for example, you got a clear. Let's say you've got a clear that is accidentally shorted to ground. This guy is counting fine, and let's say that is connected this time. This guy's counting fine. What's this guy doing? Well, he's constantly clearing. He's constantly at a 0. Okay, so you just got to go ahead and check for some of the shorts there. Okay, so opens and shorts, we discussed all that. Oh, how about this one? Maybe you got like a 3-bit counter, and you should see it go 000 all the way to 1. But you would normally expect this one to go 4 zeros, 4 ones, but you're seeing it do this. Let's say these are individual flip-flops. What's happening to that guy? Something's wrong with it. But look at the sequence that it's going. 0, 1, 0, 1, 0, 1, 0, 1. It's constantly stuck in toggle mode. So rather than it being hooked up correctly, what you've got there is maybe you've inadvertently shorted the JK inputs to that guy 2 plus 5. Or maybe they're inadvertently open. And again, TTL is assuming that those are plus 5, and it's toggling away. So go ahead and check for opens and shorts. And the other thing that's always a possibility, I hate to say it, just plain old dumbness. You know, maybe you've done something in your analysis for your counter design that you wanted to count in gray code, and you just maybe there's always human error. Always there's a limitless capacity for human error. Basically, that's all I'm saying is maybe you did something in your design that was inappropriate, and you've got it hooked up exactly the way you want it, but exactly the way you want it is not producing the values that you want. Okay, again, these things are stupid devices. They're going to do exactly what you tell them to do. If you tell them to do something wrong, they're going to do it wrong. Okay, so if you've ruled out opens and shorts, always check for human error. Okay, finally, we are going to move on to the traffic system application activity. And I just want to do a super brief discussion about this. It's a very long application here, and how they've shortened it up is the use of D flip-flops to implement our design. I'd prefer to implement it with JK flip-flops just because I'm a JK flip-flop fan, but you'll see why they didn't. Let's just draw our state diagram real quick here to show you what we're talking about again. So we've got 4 states, and it's either going to progress from one state to the next or stay in the state that it's currently in. And we'll refresh as to what the logical conditions are for them to move or to stay in their particular states. So what you've got here is these 4 states, and they're transitioning or staying in their own state according to these logical conditions. And if you remember right, TS is the short timer, TL long timer, VS is the vehicle sensor. So those are external inputs. But what also influences this transition? Well, the state that it's in. So it's present state. And that's our G1, G0, our gray code bits, our 2 gray code bits. So what we've got here is a mealy circuit because there's present condition and external variables. So this is why it wasn't implemented with JK flip-flops. Because we've got present and external, so there's 1, 2, 3, 4, 5 variables. And if we wanted to do this with 2 JK flip-flops, because these are the only 2 things that are going to change, G1 and G0, we would have to do 4 independent 5 variable K-maps, which only briefly alluded into chapter 4, that's when you've got a 4 on top of a 4, and you can do vertical grouping. So needless to say, we're not going to do that because we'd be here all day. So long story short, out of the whole thing, what I want you guys to get out of the whole thing here is just go ahead and read through that. Ultimately, what they've done is using D flip-flops made it a lot easier. So D flip-flops, given that our possible occurrences for G0 and G1, they can only transition from a 0 to a 0, 0 to a 1, 1 to a 0, and a 1 to 1. So rather than doing a separate analysis for a J and a K, all they're doing is a single analysis for the D inputs. So for a 0 to stay a 0, what's the D input? What's a 0? For a 0 to go to a 1, what's the D input? It's a 1. For a 1 to go to a 0, what's the D input? 0. For a 1 to stay a 1, what's the D input? 1. Substantially easier than doing 4 5 variable K maps. Okay, so just Take a brief look through the traffic signal control part 3 system application activity, and we are going to move on to registers.